Hello, my name is John Fortner, and this is my Lab 3 Black Hole video report. Okay, so Lab 3 Black Hole explores how to use the motion of an object to gather information about the forces acting upon that object. So in this lab, our specific case is information about the motion of a star orbiting a black hole, which we use to estimate the mass of the black hole. This lab relies on the momentum principle, specifically the idea that force is equivalent to the derivative of momentum, because we have the motion of the star, and from that we can obtain information about the force acting upon it. And using that force, we also utilize a formula for gravitational force in order to estimate the mass of the black hole. So this is the process for calculating the mass of the black hole from the velocity information in our data. So first we calculate the change in velocity delta v between our two data entries. And then from that we multiply by the mass of the star to calculate delta p, change in momentum. We divide that by delta t, the time step between the two data points, to estimate dp dt, which is the derivative of momentum. And then we set that equal to net force because the derivative of momentum is mathematically equivalent to the net force. We can assume that the black hole is the only source acting on the system, so we set F net equal to the gravitational force formula, and then rearrange that to solve for the mass of the black hole. So this is my code, which will go ahead and run. So in this model, the orange arrow represents the total net force, the blue arrow represents the perpendicular component of net force, and the pink arrow represents the parallel component of net force. And as you can see, here it calculates the magnitude of net force and then the magnitude of the parallel and perpendicular components of net force. And then this is after each loop, the program is calculating the mass of the black hole, or the estimate based on the data in that step of the index. So this is accurate, like pretty accurate, except for the first loop, which outputs a 0. And this is my actual code. So these 3 lines are just some constants that had to be inputted, 86,400 being the number of seconds in a day, which is the time step between 2 data points. So here's the actual loop, which is the meat of the code. And these are just the velocity, the final and initial velocities pulled from the data. With these, we can solve for the initial and final momentums here. And with those, we can calculate the change in momentum, delta p, and use that to estimate dp dt, which is the derivative of momentum, or the rate of change of momentum over time. And then we know that that is mathematically equivalent to net force, so we can set those equal to each other. Here we're solving for the parallel and perpendicular components of dp dt, and we can do that because using an extrapolation of the product rule of derivatives, we know that the parallel component of dp dt is equal to p hat, the direction of momentum, multiplied by the derivative of the magnitude of momentum. And then here we are using the identity dp dt is equal to dp dt parallel plus dp dt perpendicular, and just rearranging that to solve for dp dt perpendicular. This r is a vector that's just the position vector for the star, and we use that in the gravitational force formula. We have the magnitude of F net and the magnitude of R, and we just rearrange the gravitational force formula to solve for the mass of the black hole, and then print the mass of the black hole after every loop. So as for the actual results, I just took the average of all of the outputs of the loop to get an estimate for the mass of the black hole, and my average was 9.44 times 10 to the 33 kilograms. So something worth considering for this lab is the equivalence of the rate of change of momentum, dp dt, and F net. So these two are mathematically equivalent, the only difference between them being that dp dt we can obtain from the motion of the object. So you could say that it's measurable, whereas F net is not inherently measurable. So we have to use that information about the motion to calculate dp dt, and use that to sort of bridge the gap between what is measurable and using the net force to actually calculate something meaningful about the mass of the black hole. So what if question applied to this lab is if you replace the black hole with another black hole of unknown mass in the same position, and observed that the motion of the star remained unchanged, would you be able to calculate the mass of that black hole? And assuming that the motion of the star remains unchanged and the position of the black hole is the same, then the mass of the black hole must be the same, because any change to the mass of the black hole would change the orbit of the star, because it would change the gravitational force. That's all. Thank you very much.